In this video, we are going to explore, are black holes eternal? We'll dive into this topic in more detail, but if you have high-level knowledge in black holes, don't worry, I've got you covered. And if you're a science and cosmic enthusiast like me, you've come to the right place. This channel is definitely for you. By the end of this video, I promise you'll be very well informed about black holes. Let me tell you something that will blow your mind. Black holes die. Yes, you heard that right. The most powerful, most destructive, most permanent-seeming objects in the entire universe don't seem to live forever. And when Stephen Hawking figured this out back in 1974, he didn't just discover something amazing about black holes. He accidentally broke physics itself. Think about that for a second. Black holes are these cosmic monsters that devour everything. Light cannot escape them. Matter cannot escape them. Time itself gets twisted into knots around them. They seem like the ultimate forever objects, right? But Hawking discovered they slowly leak energy, they shrink, and eventually, after an impossibly long time, they vanish in a final explosion. Now here's where it gets really weird. The way black holes die creates the biggest mystery in modern science. It's a paradox so profound that scientists have been arguing about it for 50 years. Some of the smartest people on Earth have proposed solutions that sound like science fiction. Walls of fire at the edge of black holes. Our universe being a hologram. Microscopic wormholes connecting every particle in existence. You might be thinking, okay, that's interesting, but why should I care about black holes dying trillions and trillions of years from now? Well, here's why this matters to you right now, sitting here watching this video. Black holes hold the secret to whether information can be destroyed. And what is information? It's not just data on a computer. In physics, information is the complete description of everything about something. Every atom in your body, every memory in your brain, every thought you've ever had, that's all information. And there's a fundamental rule in physics that says information is eternal. It can be scrambled, mixed up, hidden, but never truly destroyed. Except black holes seem to destroy it completely. And if information can be destroyed, then everything you are, your memories, your personality, your consciousness, could one day be erased from reality so completely that it's like you never existed at all. Not just forgotten, not just gone, but erased from the fundamental fabric of the universe. This isn't some abstract philosophical question. This is about whether the laws of physics make sense, whether reality is consistent, whether the universe operates according to rules we can understand, or whether there's a place where those rules break down completely. Over the next 2.5 hours, we're going on a journey together. We're going to start by understanding what makes black holes so special and so extreme. Then we're going to discover how Hawking figured out that they die. We'll face the impossible paradox this creates, a contradiction so severe that it threatens to tear apart our understanding of reality. And finally, we'll explore the wild solutions scientists have proposed, each one stranger than the last. This is going to be like a detective story, except the mystery we're solving is about the nature of reality itself. Every answer we find will lead to deeper questions. Every solution will reveal new problems. By the end, you'll understand one of the most profound mysteries in all of science, explained in a way that anyone can grasp. But before we can understand how black holes die, we need to know what makes them so special in the first place. We need to understand why they were considered eternal for so long. So let's start at the beginning with a simple question. What exactly is a black hole? Imagine holding planet Earth in your hands. All 8 billion people, all the cities and oceans and mountains, every atom of rock and metal from the surface down to the core. Now imagine you could crush it, squeeze it smaller and smaller, forcing all that mass into a tinier and tinier space. Keep squeezing. Make it the size of a basketball. Keep going. Make it the size of a marble. Keep crushing until all of Earth fits into a space smaller than the tip of a needle. At some point during this impossible compression, something dramatic happens. The gravity becomes so intense that space and time themselves get ripped apart. You've created a black hole. This is what makes black holes so extreme. They're places where gravity has won completely, not partially, not mostly, but absolutely and totally. The matter that forms a black hole gets crushed down to a point of infinite density called a singularity. And around that point, gravity becomes so powerful that it creates a boundary called the event horizon. The event horizon is the most important feature of a black hole. Think of it as a one-way door in space. Once anything crosses that boundary, it cannot come back. Not with rockets, not with any amount of energy, not ever. And this includes light itself. Light is the fastest thing in the universe, traveling at 300 million meters per second. But even light cannot escape from inside a black hole. That's why they're called black holes, because no light can escape to tell us what's inside. Let me paint a picture for you. If you were watching someone fall toward a black hole from a safe distance away, you would see something very strange. As they got closer and closer to the event horizon, they would appear to move slower and slower. Time itself slows down near a black hole, and the closer you get, the slower time flows. To you, watching from far away, the person would seem to freeze at the edge, never quite crossing the event horizon. Their image would get dimmer and redder, but you would never see them actually go through. But here's the weird part. From the perspective of the person falling in, nothing special happens at the event horizon at all. They don't feel themselves slowing down. They don't feel a barrier. They just fall straight through in a matter of seconds. To them, it's just empty space. But once they cross that boundary, their fate is sealed. They will hit the singularity at the center, and there is no force in the universe that can stop it from happening. Here's something most people don't know. When scientists first worked out the mathematics of black holes in the early 20th century, they didn't call them black holes at all. They called them frozen stars. And that name actually tells us something really important about how strange these objects are. The idea of frozen stars comes from that time dilation effect I just mentioned. Remember how from far away you see someone falling in get slower and slower until they seem frozen at the edge? Well, imagine a massive star collapsing to form a black hole. From our perspective, watching from far away, we would never actually see the collapse finish. The surface of the star would appear to freeze just as it reaches the point of becoming a black hole. Time would slow down so much that the final moment of collapse would seem to stretch out forever. So, from the outside, a black hole looks like a star that froze at the very instant of its death. But from the perspective of the matter collapsing inward, everything happens normally. The collapse continues all the way down to the singularity. This creates two completely different descriptions of the same event. From outside, the collapse never quite finishes. From inside, it definitely does finish. Both perspectives are equally valid, but they contradict each other. This is our first hint that black holes do something very strange to reality. They create situations where two observers can have completely different but equally true descriptions of what's happening. It's like two people watching the same movie but seeing different endings, and both endings are real. This seemingly impossible situation will become very important later when we talk about the information paradox. The term black hole wasn't actually popularized until 1967, when physicist John Wheeler started using it. And honestly, it's a much catchier name than frozen star. But that old name reminds us that black holes exist at the boundary between two different realities. The reality outside, where time runs normally, and the reality inside, where the rules are completely different. Now, let's talk about where black holes actually come from. How does nature create these extreme objects? The answer lies in the life and death of stars. Stars are massive balls of gas, mostly hydrogen, that shine because they're constantly running a nuclear furnace in their cores. Inside the core of a star, hydrogen atoms are being crushed together so hard that they fuse into helium. This fusion releases enormous amounts of energy, and that energy pushes outward. At the same time, gravity is pulling everything inward. For most of a star's life, these two forces are perfectly balanced. The outward pressure from fusion exactly matches the inward pull of gravity. But here's the problem. Stars don't live forever. Eventually, they run out of hydrogen fuel. When that happens, the fusion reactions start to shut down. And when the outward pressure decreases, gravity starts to win. The star begins to collapse inward under its own weight. What happens next depends on how massive the star is. If the star is relatively small, like our Sun, it will collapse into something called a white dwarf, a dead star about the size of Earth. If it's bigger, it might collapse into a neutron star, a ball of pure neutrons about the size of a city, but containing more mass than the Sun. But if the star is really massive, more than about 20 times the mass of our Sun, then nothing can stop the collapse. The matter crushes together so tightly that it overwhelms every force trying to resist it. The star collapses all the way down into a black hole. This collapse happens fast. Once it starts, the core of the massive star crushes down to a point in less than a second. The outer layers of the star fall inward at nearly the speed of light, then bounce off the incredibly dense core and explode outward in what we call a supernova. For a few weeks, this exploding star can shine brighter than an entire galaxy. But hidden in the center, invisible and silent, a black hole has been born. These stellar mass black holes are typically between 5 and 50 times the mass of our Sun. But there's another type of black hole that's even more extreme. At the centers of most galaxies, including our own Milky Way, there are supermassive black holes. These monsters contain millions or even billions of times the mass of the Sun. The black hole at the center of our galaxy, called Sagittarius A star, contains about 4 million solar masses. The largest black holes we've discovered are over 60 billion times the mass of the Sun. We're not entirely sure how these supermassive black holes formed. They might have grown slowly over billions of years by eating gas and stars. Or they might have formed from the direct collapse of enormous clouds of gas in the early universe. But regardless of how they formed, they follow the same rules as their smaller cousins. They have an event horizon. They crush everything that falls in, and nothing escapes. For a long time, from when Einstein first developed his theory of general relativity in 1915 all the way through the middle of the 20th century, scientists believed that black holes were eternal. Once formed, they would exist forever, and the reasoning seemed absolutely solid. Think about it this way. Black holes only do one thing. They grow. Every time something falls into a black hole, it gains mass. More mass means stronger gravity, which means a bigger event horizon, which means the black hole can capture even more material. It's a one-way process. Mass goes in, but nothing comes out. Even if you stopped feeding a black hole any matter at all, scientists thought it would still survive forever. You see, according to Einstein's theory, even empty space contains a tiny amount of energy called vacuum energy. A black hole sitting in completely empty space would slowly absorb even this vacuum energy, continuing to grow, albeit very slowly. And remember, nothing can escape from inside the event horizon. Not matter, not light, not information, not anything. The event horizon is the ultimate one-way door. Once mass energy crosses that boundary, it's gone from our universe for good, added to the black hole's total mass. There seemed to be no mechanism by which a black hole could lose mass or shrink. This apparent immortality made black holes seem like the universe's ultimate winners. Stars burn out, planets crumble, even atoms can decay. But black holes, they just keep going, growing slowly larger, absorbing everything around them. Given enough time, an incomprehensible amount of time, black holes would be the only structures left in the entire universe. Everything else would eventually fall into them or decay away. Physicists worked out what this far future would look like. Long after the last stars burned out, long after every galaxy went dark, there would be only black holes drifting through the void. And then, nothing would happen. Forever. The universe would be frozen in a state of maximum entropy, with black holes as the only remaining objects locked in place for eternity. It was a dark vision of the future, but it seemed inevitable based on everything we understood about physics. The laws of thermodynamics, the principles of general relativity, the mathematics of black holes, they all pointed to the same conclusion. Black holes are eternal. But in 1974, a young British physicist named Stephen Hawking was thinking about black holes in a new way. He wasn't just using general relativity to understand them. He was thinking about what happens when you combine general relativity with another fundamental theory of physics called quantum mechanics. And when he did that calculation, he discovered something that shocked everyone, including himself. Stephen Hawking was 32 years old in 1974. He was already well known among physicists for his work on black holes and cosmology, despite being severely disabled by a disease called ALS. His body was failing, but his mind was sharper than ever. And that year he asked a question that nobody had quite asked before. The question was simple: what happens to quantum mechanics near a black hole? Now, this might not sound like a revolutionary question, but it was. You see, physics in the 20th century was dominated by two great theories. General relativity, developed by Einstein, describes gravity and the large-scale structure of space and time. It works incredibly well for big objects, planets, stars, black holes, the universe itself. Quantum mechanics, developed by many scientists in the 1920s and 30s, describes the behavior of very small things: atoms, electrons, photons. It works incredibly well at tiny scales. But here's the problem. These two theories don't play nice with each other. When you try to use both of them together in the same calculation, you often get nonsensical answers. Infinities pop up. Contradictions appear. For most practical purposes, this doesn't matter because gravity is important for big things and quantum mechanics is important for small things, and rarely do you need both at once. But black holes are different. Black holes are both big and small at the same time. They contain huge amounts of mass, so gravity is incredibly strong. But all that mass is crushed down to an infinitely small point, where quantum effects should be important. Black holes are the places in the universe where general relativity and quantum mechanics meet head-on. Hawking decided to think carefully about what quantum mechanics says about empty space near a black hole's event horizon. And what quantum mechanics says about empty space is actually pretty weird. According to quantum mechanics, empty space isn't truly empty. It's filled with something called quantum fluctuations. Here's how that works. In the quantum world, energy can be borrowed from nothing for very short periods of time. Pairs of particles suddenly pop into existence out of empty space, one particle and one antiparticle. They exist for a tiny fraction of a second, then crash back together and annihilate, paying back the borrowed energy. This happens everywhere, all the time. Empty space is actually boiling with these virtual particle pairs constantly appearing and disappearing. Under normal circumstances, we never notice these virtual particles because they exist for such a short time and disappear so quickly. But Hawking realized that something very interesting would happen to these virtual particle pairs near a black hole's event horizon. Picture this in your mind. Virtual particle pairs are constantly popping into existence near the event horizon of a black hole. These pairs appear just outside the horizon, in the region of space where you can still escape if you move fast enough. Under normal circumstances, these particle pairs would annihilate each other almost instantly and disappear. But sometimes, just by chance, one of the particles appears just slightly closer to the black hole than its partner. And if it appears close enough that one particle might fall across the event horizon before the pair can recombine. The particle that fell in is now trapped forever. It will never come back out. But here's the crucial part. The other particle, the one that didn't fall in, is now left all alone. Normally, it would have annihilated with its partner, but its partner is gone, trapped behind the event horizon. So this particle becomes real. It escapes into space. To an outside observer, it looks like the black hole just emitted a particle. Now you might think, okay, so a particle escaped from near the black hole. But you said nothing can escape from a black hole. And you'd be right to be confused. The key insight is that the particle didn't come from inside the black hole. It was created just outside the event horizon. So technically, nothing escaped from inside. But from far away, it looks like the black hole is glowing, emitting particles into space. This is called Hawking radiation, and it's named after the man who discovered it. But here's where it gets really interesting. Remember that virtual particle pairs borrow energy to exist. When one of the particles falls into the black hole, it actually has negative energy from the black hole's perspective. This is hard to wrap your mind around, but it's a consequence of the mathematics. The particle that fell in reduces the black hole's mass slightly. Meanwhile, the particle that escaped has positive energy. It carries energy away from the black hole. So from the outside, it looks like the black hole is radiating energy into space. And since energy and mass are equivalent according to Einstein's famous equation E equals mc squared, losing energy means losing mass. When Hawking first worked this out, even he didn't believe the result. He spent months checking and rechecking his mathematics, looking for an error. He thought he must have made a mistake somewhere because the conclusion was too shocking. Black holes emit radiation. Black holes lose mass. Black holes shrink. After checking everything multiple times and finding no errors, Hawking announced his discovery at a scientific conference. The reaction was immediate and intense. Many physicists simply didn't believe him. Some thought he had made a mathematical error. Others thought the effect must be so small that it didn't matter. The chairman of the session, a physicist named John Taylor, publicly announced that Hawking was completely wrong. But over the following months and years, other physicists checked Hawking's calculations. They used different methods, different approaches, different mathematical techniques, and every single calculation came to the same conclusion. Hawking was right. Black holes emit radiation, and if they emit radiation, they lose energy. And if they lose energy, they lose mass. And if they lose mass, they shrink. Black holes are not eternal after all. They evaporate. They die. And when Hawking realized what this meant, when he worked through all the implications, he discovered something even more disturbing. But we'll get to that. First, let's understand exactly how this Hawking radiation works and what it means for the fate of black holes. The year was 1974, and the world of theoretical physics was about to be turned upside down. When Stephen Hawking first announced that black holes emit radiation at a conference in Oxford, the response was a mixture of disbelief, confusion, and outright skepticism. Here was this young physicist claiming that the most fundamental assumption about black holes, that nothing escapes them, was wrong. What made the announcement even more shocking was that Hawking himself had spent months doubting his own result. He told colleagues later that when he first derived the equations showing that black holes radiate, he thought he had made a terrible mistake. He checked his work over and over, approaching the problem from different angles, using different mathematical techniques. Every time he got the same answer: black holes glow. The chairman of that Oxford conference, physicist John Taylor, stood up after Hawking's presentation and declared that it was nonsense. Other senior physicists in the audience shook their heads. Some walked out. The idea seemed to violate everything they knew about black holes. The event horizon was supposed to be a one-way door. Nothing comes out. That was the whole point of a black hole. But here's the thing about good science. It doesn't matter how counterintuitive an idea seems. It doesn't matter how much it contradicts your expectations. If the mathematics is correct, if the physics is sound, then nature doesn't care about your intuition. And Hawking's mathematics was impeccable. Over the following year, other physicists around the world began checking Hawking's calculations. They used different approaches. Some used quantum field theory in curved space-time. Others used thermodynamic arguments. Some used semi-classical approximations. The specific techniques varied, but the conclusion was always the same. Hawking was absolutely right. Black holes emit thermal radiation, and this radiation carries away energy, causing the black hole to slowly evaporate. By 1975, the scientific community had accepted Hawking's result. It wasn't just accepted, it was celebrated as one of the most important discoveries in theoretical physics of the 20th century. Hawking had revealed a deep connection between gravity, quantum mechanics, and thermodynamics that nobody had suspected. He had shown that black holes weren't the simple eternal objects people had imagined. They were dynamic, evolving, and ultimately mortal. Let's go back to that picture of virtual particle pairs appearing near the event horizon, but let's think about it more carefully this time. I want you to really understand what's happening here, because it's both beautiful and bizarre. Everywhere in the universe, at every point in space, quantum mechanics tells us that particle-antiparticle pairs are constantly blinking into existence. An electron and a positron, a quark and an antiquark, a photon and another photon. These pairs appear out of nothing, exist for an incredibly brief moment, and then collide and annihilate, disappearing back into nothing. This happens because quantum mechanics allows energy to be borrowed from the vacuum for very short times, as long as it's paid back quickly. The energy borrowed to create these virtual particles comes from the quantum uncertainty of empty space itself. According to Heisenberg's uncertainty principle, you can never know both the energy and the time of a quantum system with perfect precision. This uncertainty means that for very short time intervals, energy can fluctuate wildly, allowing particle pairs to pop into existence as long as they disappear quickly enough that nobody notices the violation of energy conservation. Under normal circumstances, this quantum foam of virtual particles has no noticeable effect on anything. The particles exist for such short times and at such small scales that they're completely invisible to us. But black holes change everything. When these virtual particle pairs appear right at the edge of a black hole's event horizon, something dramatic can happen. Imagine a particle-antiparticle pair popping into existence just barely outside the horizon. One particle appears slightly closer to the black hole, the other slightly farther away. In normal space, both particles would quickly fall back together and annihilate. But near a black hole, the gravitational pull is so strong that it can separate the pair before they have a chance to recombine. The particle closer to the black hole gets pulled across the event horizon and falls in. Once it crosses that boundary, it's gone forever. It can never come back out to annihilate with its partner. The other particle, the one that was farther from the black hole, is now left alone. It has been separated from its partner by the event horizon. And here's the key point. Because it can no longer annihilate with its partner, it becomes a real particle. It's no longer a temporary quantum fluctuation. It's a permanent particle that can escape into space. From far away, if you're watching the black hole, you would see particles streaming away from it. You would see the black hole glowing with radiation. It would look like the black hole is emitting particles, even though nothing actually came from inside the event horizon. The particles are being created right at the edge. Now here's where it gets really clever. The particle that fell into the black hole has negative energy from the black hole's perspective. This sounds weird, but it makes sense if you think about it. The particle was created by borrowing energy from the quantum vacuum. When the pair was separated, one particle took positive energy and escaped, while the other took negative energy and fell in. The black hole has to pay for the positive energy of the escape particle, and it pays by accepting the negative energy of the infalling particle. Negative energy means negative mass. So every time a particle escapes as Hawking radiation, the black hole loses a tiny bit of mass. It gets smaller. And this process continues constantly, every moment, as long as the black hole exists. The black hole is slowly paying off an energy debt to the universe, one particle at a time. One of the most beautiful and strange aspects of Hawking's discovery is that black holes have a temperature. Just like a hot stove or a star, black holes emit thermal radiation with a specific temperature. But the relationship between a black hole's size and its temperature is completely backwards from what you might expect. In normal physics, bigger things cool down slower. A big pot of water takes longer to cool than a small cup. A massive star is hotter than a small star. But black holes are the opposite. Smaller black holes are hotter than big ones. Here's the formula Hawking derived. The temperature of a black hole is inversely proportional to its mass. Double the mass and you halve the temperature. Make it 10 times more massive and it becomes 10 times cooler. This inverse relationship comes from the mathematics of quantum field theory in curved space-time, but we can understand why it makes sense. Think about the event horizon. For a big black hole, the event horizon is a huge sphere with very gentle curvature. Virtual particle pairs appearing near this horizon have plenty of space to exist before potentially being separated. For a small black hole, the event horizon is tiny with very sharp curvature. The gravitational tidal forces are much more intense, and virtual particle pairs are much more likely to be ripped apart before they can annihilate. So small black holes produce Hawking radiation much more efficiently than large black holes. And more radiation means higher temperature. Let's put some actual numbers on this because the temperatures are extreme. Consider a black hole with the mass of our Sun. This is about the smallest black hole that could form from a collapsing star. According to Hawking's formula, this black hole would have a temperature of about 1/10,000,000th of a degree above absolute zero. That's incredibly cold, much colder than empty space, which still has the cosmic microwave background radiation at about 3 degrees above absolute zero. A solar mass black hole is actually colder than the space around it, so it absorbs more radiation than it emits, and it actually grows rather than shrinking. Now, consider the supermassive black hole at the center of our galaxy, with its 4 million solar masses. This black hole has a temperature of about 100 billionth of a degree above absolute zero. It's so cold that its Hawking radiation is essentially invisible. But here's where it gets interesting. As a black hole loses mass through Hawking radiation, it shrinks. And as it shrinks, its temperature goes up. The process accelerates. A smaller, hotter black hole radiates more energy, which makes it shrink faster, which makes it hotter still, which makes it radiate even more energy. It's a runaway process. In the final stages of a black hole's life, when it's shrunk down to a tiny mass, it becomes incredibly hot. We're talking about temperatures of billions or even trillions of degrees. At these temperatures, the black hole isn't just emitting individual particles anymore. It's emitting massive bursts of energy. And in its final moment, something spectacular happens. Let's talk about time scales, because when we're discussing black hole evaporation, we're dealing with numbers that are almost impossible to comprehend. I want to give you a real sense of just how long it takes for a black hole to evaporate completely. The evaporation time depends on the black hole's mass. Hawking worked out a formula that tells us exactly how long it takes. The evaporation time is proportional to the cube of the mass. Double the mass, and it takes 8 times longer to evaporate. 10 times the mass means 1,000 times longer. This cubic relationship means that even small differences in mass lead to enormous differences in lifetime. Let's start with a hypothetical small black hole, say about the mass of a mountain, roughly 1 billion tons. This isn't a black hole that could form naturally. A collapsing star creates black holes with at least 3 solar masses, But imagine we somehow created a mountain-mass black hole artificially. How long would it take to evaporate? The answer is about 1 billion years. That sounds like a long time, and it is. It's about a quarter of the age of Earth. But in cosmic terms, it's actually pretty quick. Such a black hole would have evaporated long ago if any existed in our universe. Now let's consider a real black hole, one formed from the collapse of a massive star. Let's say it has 10 times the mass of the Sun. This is on the small end for stellar black holes, but it's a realistic number. How long would this black hole take to evaporate completely? Get ready for this. The answer is about 10 to the power of 67 years. Let me spell that out. It's a 1 followed by 67 zeros. To put that in perspective, the universe is currently only about 14 billion years old. That's about 10 to the power of 10 years. This black hole would last about 10,000 trillion times longer than the universe has currently existed. Let's go bigger. Consider a supermassive black hole like the one at the center of our galaxy, 4 million solar masses. The evaporation time for this monster is about 10 to the power of 99 years. These numbers are so large they become almost meaningless. There's no way to really visualize or understand time scales this vast. And if we consider the most massive black holes in the universe, the ones at the centers of the largest galaxies weighing in at tens of billions of solar masses, their evaporation times stretch to 10 to the power of 100 years or more. These are numbers with 100 zeros after them. To put this in context, by the time these black holes evaporate, the universe will be unrecognizably different. All the stars will have burned out, all the planets will have crumbled to dust, even the protons and neutrons that make up ordinary matter might have decayed into radiation. The universe will be a cold, dark, empty void, with just these black holes slowly evaporating. But here's what's important. No matter how long it takes, the evaporation does happen. Black holes are not eternal. Given enough time, an amount of time that makes the age of the universe seem like the blink of an eye, every black hole will evaporate completely. Now let's zoom in on the end of a black hole's life, because this is where things get truly spectacular. We've established that black hole evaporation is a runaway process. As the black hole shrinks, it gets hotter. As it gets hotter, it radiates more energy. As it radiates more energy, it shrinks faster. This feedback loop means that the evaporation accelerates as it proceeds. For most of a black hole's life, and we're talking about 99.999999% of its existence, the evaporation is extremely slow and steady. The black hole sits there, barely glowing, losing mass at an imperceptible rate. But in the final moments, everything changes. When a black hole has shrunk down to about the mass of a large asteroid, its temperature has climbed to billions of degrees. It's now radiating intensely in all forms of energy, gamma rays, X-rays, particles of all types. It's not just gently glowing anymore, it's blazing. As it continues to shrink, the temperature keeps rising. 10 billion degrees, 100 billion degrees, 1 trillion degrees. At these temperatures, the black hole starts emitting not just individual particles, but massive bursts of high-energy radiation. It's radiating away its remaining mass at an incredible rate. In the final second of a black hole's life, it releases as much energy as a large star releases in its entire lifetime. Imagine that. A trillion years of patient, slow evaporation. And then, in the last second, it all happens at once. It's like a star going supernova, except instead of a star's worth of matter exploding, it's a black hole's worth of energy exploding. The black hole shrinks smaller and smaller, hotter and hotter, brighter and brighter. And then, in a final flash of gamma rays and elementary particles, it disappears. The singularity at its center vanishes. The event horizon collapses to nothing. Where there was once a black hole, there's now just empty space and a burst of radiation expanding outward at the speed of light. And here's the eerie part. When that black hole vanishes, nobody nearby would have any idea what had been there. The final explosion releases a lot of energy, sure, but in the vastness of space, even a black hole-sized energy release gets diluted very quickly. By the time that energy pulse has travelled a light year, it's spread out over an enormous volume of space. It would be almost undetectable. So picture this. In the unimaginably distant future, after the last stars have gone dark, after the universe has aged beyond recognition, isolated black holes will be floating in the void. And one by one, after incomprehensible ages, they will wink out of existence in final bursts of light that nobody will be there to see. But here's where Hawking's discovery stops being just interesting and starts being disturbing. When Hawking worked out the detailed properties of the radiation that black holes emit, he realized it had a very troubling feature. And this feature creates what's called the black hole information paradox. A contradiction so profound that it threatens our entire understanding of how physics works. When Stephen Hawking calculated the exact properties of the radiation emitted by black holes, he discovered something deeply unsettling. The radiation is completely random. It's thermal radiation, like the glow from a hot piece of metal. And thermal radiation contains no information about what created it. Let me explain what I mean by that. Imagine you heat up a piece of iron until it glows red hot. The light it emits is thermal radiation. Now imagine you heat up a piece of copper to the same temperature. It also glows, and the glow looks identical. You cannot tell by looking at the light whether it came from iron or copper. The thermal radiation has lost all the specific information about what material was heated. Hawking radiation is exactly like this. According to Hawking's calculations, a black hole emits particles with a thermal spectrum, a characteristic pattern of energies that depends only on the black hole's temperature. And the temperature depends only on the black hole's mass. Nothing else matters. So here's the problem. Imagine you throw a book into a black hole. That book contains information, the words on its pages, the type of paper, the ink composition, everything. Then you throw in a computer with completely different information. Then you throw in a basketball. Then a grand piano. The black hole grows very slightly with each thing you add, but all this stuff just adds to its total mass. Now, fast forward trillions upon trillions of years. The black hole evaporates completely via Hawking radiation. According to Hawking's calculations, that radiation will be completely thermal and random. It will contain no information whatsoever about the book, the computer, the basketball, or the piano. That information appears to be gone, vanished, destroyed completely. You might be thinking, so what? Things get destroyed all the time. If I burn a book, the information in it is destroyed, right? Wrong. And this is where we need to talk about what information really means in physics, because it's one of the most fundamental concepts in all of science. In everyday language, we use the word information to mean facts or knowledge. But in physics, information has a very specific and precise meaning. Information is the complete description of the quantum state of a system. It's everything about something. The position, momentum, spin, and every other property of every single particle. Let me give you an example. Consider a single atom. To completely describe that atom in physical terms, you need to specify its quantum state. Where is its nucleus? How are its electrons arranged? What is their spin? What is their energy? All of these properties together constitute the information contained in that atom. Now scale this up. A book contains roughly 10 to the power of 25 atoms. To completely describe that book in physical terms, you would need to specify the quantum state of every single one of those atoms. That's an enormous amount of information, far more than just the words printed on the pages. It includes the exact position of every molecule, the thermal motion of every atom, the quantum states of every electron. All of that together is the information in the book. Here's the crucial principle that underlies all of quantum mechanics and indeed all of physics. Information is conserved. It can be scrambled, hidden, or spread out, but it can never be destroyed. This is as fundamental to physics as the conservation of energy. In fact, the conservation of information is deeply connected to the conservation of energy through the mathematics of quantum mechanics. Let me give you an example of information being scrambled but not destroyed. Suppose you burn a book. The book turns to ash and smoke. The words are gone. The pages are destroyed. In everyday terms, we'd say the information was lost. But a physicist would disagree. All the atoms that made up the book still exist. They're now in the ash and smoke, and they're mixed with oxygen atoms from the air. If you could track every single atom and photon produced by the burning, if you could measure their exact quantum states, you could in principle reconstruct what the book said. This seems impossible, right? How could you possibly track all those atoms and figure out what the book said from looking at ashes? Well, you can't do it practically. It would require measuring the quantum state of about 10 to the power of 25 particles with perfect precision, and then doing an impossibly complex calculation. But the point is that the information is still there in principle. It's scrambled beyond recognition, spread out among countless particles, but it exists. Given perfect knowledge of the quantum states of all those particles and unlimited computational power, you could reconstruct the original book. This is true for every physical process we know about. You crack an egg, and the information about how it was arranged gets scrambled into the proteins and lipids of the scrambled egg. But it's still there in principle. You mix cream into coffee, and the information about which molecules were cream and which were coffee gets scrambled, but it's still there. A star explodes in a supernova, and all the information about the arrangement of atoms in that star gets scattered across space in the debris, but it's not destroyed. The conservation of information is related to a property called unitarity in quantum mechanics. Unitarity means that quantum evolution is reversible. If you know the exact quantum state of a system at one time, you can calculate what it was at any earlier time and what it will be at any future time. The mathematics works both forward and backward. Information cannot appear from nowhere, and it cannot disappear into nothing. This principle has been tested countless times in countless ways, and it has never been violated. Every experiment we've ever done confirms that information is conserved. It's one of the bedrock principles on which all of modern physics is built. If information could be destroyed, quantum mechanics would be wrong. The mathematics wouldn't work. The theory would have to be thrown out and replaced with something else. Now we can understand the full horror of the information paradox. Let's walk through it step by step, slowly and carefully, because this is the heart of the mystery. Step 1. You throw something with information into a black hole. Let's use that book again as our example. The book contains information, the quantum states of all its atoms. The book crosses the event horizon and falls into the black hole. From the outside, that information is now hidden behind the event horizon. You can't see it, you can't access it, but it still exists. It's inside the black hole. Step 2. Time passes. A lot of time. Trillions upon trillions upon trillions of years. The black hole slowly evaporates through Hawking radiation. It gets smaller and smaller, hotter and hotter. Finally, it vanishes in a final burst of radiation. Step 3. We examine the radiation that came out. According to Hawking's original calculation, this radiation is completely thermal. It's random. It has no correlation whatsoever with what fell into the black hole. You could have thrown in a book or a computer or a piano, and the radiation would be statistically identical. Step 4. The paradox emerges. Where did the information go? The book's information cannot be inside the black hole anymore because there is no black hole. It all evaporated away. But the information also doesn't appear to be in the Hawking radiation because that radiation is thermal and random. So the information has vanished from the universe completely. But this is impossible according to quantum mechanics. Information cannot be destroyed. If it was in the book and the book fell into the black hole, then that information must still exist somewhere. Either it's still inside the black hole somehow, or it came out in the radiation, or what? There's no third option that makes sense. This is a direct contradiction between two of our most successful theories of physics. General relativity, which describes black holes, says that information can fall behind an event horizon and then disappear when the black hole evaporates. Quantum mechanics says that information can never be destroyed under any circumstances. Both of these theories have been tested extensively, and both work perfectly in their respective domains. But they cannot both be right about black holes. Something has to give. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and something about our understanding of black holes is incomplete. Or both theories are wrong and we need a completely new theory to replace them. This is not a minor puzzle. This is not some technical detail that only matters to specialists. This goes to the very heart of whether we understand how the universe works at its most fundamental level. And for 50 years, physicists have been trying to solve it. You might still be thinking, okay, but this is just about black holes. Black holes are rare and far away. Why should I care about a paradox involving objects I'll never encounter? Let me tell you why this matters profoundly, not just for physics, but for understanding the nature of reality itself. First, let's think about what it means for information to be destroyable. Information, in the physical sense, isn't just abstract data. It's the complete description of reality. Every particle, every field, every quantum state, all of that is information. And you, sitting there right now, are made of information. Your body is about 10 to the power of 28 atoms. Your brain contains about 10 to the power of 11 neurons, with 10 to the power of 15 connections between them. All of that physical structure corresponds to information. Now, your consciousness, your thoughts, memories, personality, all of that emerges from the physical configuration of your brain. It's encoded in the pattern of connections between neurons, the strengths of synapses, the chemical states of brain cells. All of that is information. Your mind is a pattern of information instantiated in physical matter. If information can be destroyed, then consciousness can be destroyed. Not just that you die and your body decays, we all know that happens, but that you could be erased so completely that it's as if you never existed at all. Every memory, every thought, every experience could be wiped from reality so thoroughly that no trace remains anywhere in the universe. The conservation of information suggests that even after death, even after your body decays, the information that was you still exists somewhere, somehow, scrambled into the atoms that made you up, and the photons you emitted, and every particle you ever interacted with. But if black holes can destroy information, then that's not true. You could fall into a black hole and be completely, utterly, permanently erased. And if black holes can destroy information, then maybe other processes can too. Maybe information destruction happens all the time in ways we haven't discovered yet. Maybe the universe is constantly erasing its own history. Second, this matters because it tells us that our theories of physics are incomplete. We have two great theories, general relativity and quantum mechanics, and they work incredibly well within their own domains. But the black hole information paradox reveals that when you try to combine them, you get nonsense. This means we're missing something fundamental about how the universe works. Think about it. Physics is supposed to describe reality. It's supposed to tell us the rules by which the universe operates. But we have two sets of rules that contradict each other under certain circumstances. That's like having a math textbook where one chapter says 2 + 2 = 4 and another chapter says 2 plus 2 equals 5. Both chapters can't be right. There's a deeper truth we're not seeing. The resolution of the information paradox will require a new theory that successfully unites quantum mechanics and general relativity. This theory, whatever it is, will likely change our understanding of space, time, matter and energy. It will reveal new physics that we can't even imagine yet. And the black hole information paradox is the CLU that tells us where to look. Let me make the paradox even worse by introducing another angle that makes the contradiction even more stark. In quantum mechanics, there's a theorem called the no-cloning theorem. It states simply that you cannot make an exact copy of an unknown quantum state. You cannot clone quantum information. This isn't a limitation of our technology. It's a fundamental principle that follows directly from the mathematics of quantum mechanics. The reason is subtle but important. In quantum mechanics, measuring something changes it. If you try to copy an unknown quantum state, you would need to measure it to find out what it is. But measuring it would disturb it. You can never get all the information out without destroying the original state. Now, here's how this relates to black holes. According to general relativity, information that falls into a black hole stays inside the black hole. It's behind the event horizon, forever hidden from the outside universe, but still existing inside. From the perspective of someone falling into the black hole, nothing special happens at the event horizon. They carry the information with them as they fall toward the singularity. But according to Hawking's calculation, the information must also eventually come out in the Hawking radiation. If information is conserved and the black hole completely evaporates, then all the information must be in the radiation. Do you see the problem? The information appears to be in two places. It's inside the black hole, carried by the infalling matter, and it's outside the black hole, encoded in the Hawking radiation. The same information exists in two places simultaneously. But this violates the no-cloning theorem. Quantum information cannot be copied. So we have a trilemma. Three principles that cannot all be true simultaneously. 1. Information that falls into a black hole is actually inside the black hole. 2. Information is conserved, so it must come out in the Hawking radiation. 3. Quantum information cannot be cloned. If 1 and 2 are true, then 3 is violated because the information has been cloned. If 1 and 3 are true, then 2 is violated because the information doesn't come out. If 2 and 3 are true, then 1 is violated, and the information was never really inside the black hole. Something has to give. One of these three well-established principles of physics must be wrong when it comes to black holes. But which one, and how? And what does that tell us about the nature of reality? When Stephen Hawking first discovered the information paradox in the 1970s, he proposed a radical solution. Maybe, he suggested, information can be destroyed. Maybe quantum mechanics needs to be modified. Maybe the conservation of information is not absolute after all. This was a bombshell. Hawking was essentially saying that one of the most fundamental principles in all of physics, might be wrong. And he wasn't just some crackpot making wild claims. He was one of the most respected physicists in the world, and he had the mathematics to back up his position. Hawking's argument went like this. The mathematics of Hawking radiation shows clearly that the radiation is thermal and random. There's no room in the calculation for information to be encoded in the radiation. The radiation depends only on the black hole's mass, charge, and spin, nothing else. A black hole that formed from a collapsed star emits exactly the same radiation as a black hole that formed from a pile of rocks or a cloud of gas or anything else with the same total mass, charge, and spin. This suggests strongly that the information about what fell in really is lost. And if information is lost, then quantum mechanics must be modified to allow for information destruction under extreme circumstances. Perhaps, Hawking suggested, quantum mechanics works perfectly well under normal conditions but breaks down near black holes where gravity is incredibly strong. Many physicists found this suggestion deeply disturbing. Quantum mechanics is not just some random collection of rules. It's a beautifully consistent mathematical framework. If you start modifying it to allow information destruction, the whole theory threatens to fall apart. You would lose unitarity, which is central to the mathematical structure of quantum mechanics. Probability would no longer be conserved. The theory would stop making sense. But Hawking stuck to his position for almost 30 years. The mathematics seemed clear. Black holes destroy information. Quantum mechanics needs to be revised. That was his answer to the paradox. And many physicists reluctantly agreed with him, even though they didn't like the implications. In 1997, Stephen Hawking made a famous bet with fellow physicist Kip Thorne and physicist John Preskill. The bet was simple. Hawking and Thorne bet that information is destroyed in black holes. Preskill bet against. He argued that information must be conserved somehow. The stakes were an encyclopedia of the winner's choice, to be given to the loser. For years, the bet remained unresolved. But Hawking kept thinking about the problem, and other physicists kept working on it too. New ideas were being developed. String theory was suggesting that maybe black holes were more complicated than general relativity indicated. The holographic principle was suggesting that maybe information never really goes inside a black hole at all. Then, in 2004, at a conference in Dublin, Hawking made a dramatic announcement. He had changed his mind. He now believed that information is conserved in black holes. He conceded the bet to John Preskill and gave him an encyclopedia of baseball. Preskill is a big baseball fan. The announcement made headlines around the world. Hawking admits he was wrong about black holes. But here's the thing. Hawking didn't just admit he was wrong. He claimed to have an argument for why information is conserved. Unfortunately, his argument was quite technical and not entirely convincing to most physicists. Many people felt he had conceded the bet more on philosophical grounds than because he had truly solved the paradox. See, Hawking's reasoning was something like this. If information really could be destroyed, it would violate the very foundations of quantum mechanics. This would have consequences far beyond black holes, it would affect our understanding of all quantum processes. And since quantum mechanics works so well in every other context, it seems more likely that our understanding of black holes is incomplete, rather than that quantum mechanics itself is wrong. In other words, Hawking made a judgment call. Between modifying quantum mechanics and modifying our understanding of black holes, it seems more reasonable to modify our understanding of black holes. But he didn't have a complete solution. He didn't show how information escapes from black holes. He just argued that it must escape somehow. This was unsatisfying to many physicists. Conceding that information is conserved is fine, but it doesn't solve the paradox. It just moves the mystery. Now, the question becomes, how is information conserved? By what mechanism does the information get out of the black hole and into the Hawking radiation? What are we misunderstanding about black holes that makes it seem like information is destroyed when actually it isn't? These questions remain at the cutting edge of theoretical physics today. And physicists have proposed some truly wild solutions. Solutions that challenge our basic understanding of space, time, and reality itself. Let's look at some of these proposals because they're absolutely mind-blowing. In 2012, 40 years after Hawking's original discovery, a group of physicists dropped a bomb on the black hole community. They proposed something called the firewall hypothesis, and it's one of the most dramatic and controversial ideas in recent physics. Here's the setup. Remember the equivalence principle from Einstein's general relativity. It says that falling in a gravitational field is indistinguishable from floating freely in space. If you were in a windowless room, you couldn't tell the difference between floating in deep space and falling freely in a gravitational field. This principle is fundamental to general relativity. It's what tells us that the event horizon of a black hole should be smooth and uneventful. Someone falling through it shouldn't notice anything special happening at that moment. But the firewall hypothesis says this might be wrong. The four physicists who proposed it, Ahmed Al-Mhairi, Donald Marolf, Joseph Polchinski, and James Sully, sometimes called AMPS after their initials, argued that if information is conserved, there must be a firewall at the event horizon. What's a firewall? It's a region of incredibly intense energy right at the event horizon. According to this hypothesis, anything that falls through the event horizon doesn't smoothly pass through. Instead, it hits this wall of energy and is incinerated instantly, burned to a crisp, completely destroyed. Now, you might be thinking, wait, that sounds like a solution to the information paradox, right? The information doesn't fall in. It gets burned up at the event horizon and released as radiation. But here's the problem. This contradicts the equivalence principle. It says there is something special about the event horizon. It's not just empty space. It's a death trap. Let me explain the AMPS argument more carefully because it's really clever and disturbing. They started by assuming three things that most physicists believe are true. 1. Information is conserved. 2. Hawking radiation comes from the region just outside the event horizon. 3. There's nothing special about the event horizon to someone falling through. The equivalence principle holds. Then they showed mathematically that you cannot have all three of these things be true simultaneously. It's impossible. The mathematics won't allow it. So at least one of these three principles must be wrong. If you insist on keeping the equivalence principle, then either information is destroyed or the Hawking radiation doesn't come from near the horizon. If you insist that information is conserved and radiation comes from near the horizon, then the equivalence principle must be violated. There's no way out. The AMPS group chose to sacrifice the equivalence principle. They argued that maybe there really is something special about the event horizon, a firewall that destroys anything crossing it. The information that would have fallen in gets burned up in the firewall and released as radiation. Information is conserved because it never actually went inside in the first place. But this solution is troubling. The equivalence principle is not some minor detail. It's central to general relativity. If it's violated at black hole horizons, then we don't understand gravity as well as we thought. Moreover, the firewall creates new paradoxes of its own. Where does the energy for the firewall come from? How exactly does it form? The mathematics suggests it must exist, but doesn't really explain what it is or why it's there. The firewall hypothesis ignited fierce debate. Some physicists think it might be correct. Others think it's completely wrong. Still others think it's pointing towards some deeper truth that we don't understand yet. But everyone agrees on one thing. If there really is a firewall at the event horizon, our understanding of black holes needs major revision. The holographic principle. Now let me tell you about one of the most bizarre and beautiful ideas in modern physics, the holographic principle. This idea suggests that our three-dimensional reality might be an illusion, a projection from a two-dimensional surface, and it might hold the key to solving the information paradox. The holographic principle came from work by physicists Gerard Hooft and Leonard Susskind in the 1990s. They were thinking about black holes and information, and they realized something profound. Maybe information about the inside of a black hole never actually goes inside at all. Maybe it's encoded on the surface, on the event horizon itself. To understand this, let me explain what a hologram is. You've probably seen holograms on credit cards or in science museums. A hologram looks three-dimensional, even though it's stored on a two-dimensional surface. All the information about the three-dimensional image is encoded in patterns on the flat surface. When light hits that surface the right way, it recreates the appearance of a three-dimensional object. Now imagine this same principle applied to black holes. When something falls toward a black hole, maybe it doesn't actually pass through the event horizon into some interior space. Instead, maybe it gets smeared across the event horizon, like a bug hitting a windshield. All the information about that object gets encoded in subtle patterns on the two-dimensional surface of the event horizon. From the outside, it would look like things are falling into a three-dimensional volume inside the black hole. But that would be an illusion. The reality would be that everything is encoded on the two-dimensional surface. The inside of the black hole would be like the three-dimensional image in a hologram. It appears to exist, but it's really just a projection from the surface. This solves the information paradox in a clever way. The information never goes inside, so there's no mystery about how it gets out. It was always on the surface of the event horizon. When the black hole evaporates, the Hawking radiation comes from the surface, and it carries away the information that was encoded there. Information is conserved because it never actually went anywhere. But the holographic principle goes far beyond just black holes. Physicists realized that if this works for black holes, it might work for the entire universe. Maybe our three-dimensional universe is itself a hologram projected from a two-dimensional surface at the edge of space. Maybe the depth you see, the volume you move through, the 3 dimensions you experience, maybe all of that is an illusion. Maybe reality is fundamentally two-dimensional, and three-dimensionality is just how we perceive it. This sounds like crazy science fiction, but it's actually supported by serious mathematics. In string theory, physicists have found exact mathematical correspondences between theories in three-dimensional space and theories on two-dimensional surfaces. They can do calculations in 3 dimensions, then do equivalent calculations in 2 dimensions, and get the same answers. It's as if the 3-dimensional universe and the 2-dimensional boundary are 2 descriptions of the same reality. Think about what this means for a moment. You feel like you're moving through 3-dimensional space, right? You can move forward and backward, left and right, up and down. But according to the holographic principle, this is an illusion. The real reality is 2-dimensional, and your experience of 3-dimensionality is like watching a movie. The movie feels 3-dimensional and immersive, but it's really just patterns of light on a flat screen. Your brain, your thoughts, your entire existence would be encoded in information on a 2-dimensional surface unimaginably far away. And yet you experience yourself as a 3-dimensional being moving through 3-dimensional space. The hologram is so perfect that you cannot tell the difference between the projection and real 3-dimensional reality. This has profound implications. It suggests that space itself might not be fundamental. Space might be emergent. It arises from something more basic. Just like temperature emerges from the motion of molecules but isn't a fundamental property itself, maybe space emerges from information encoded on surfaces. The universe at its deepest level might not be about space and matter at all. It might be about information and its transformations. String theory is one of the leading candidates for a theory that unites quantum mechanics and general relativity. In string theory, the fundamental building blocks of reality aren't particles. They're tiny, vibrating strings of energy. Different vibration patterns of these strings correspond to different particles: electrons, quarks, photons, everything. String theorists have been working on the black hole information paradox for decades, and they've proposed some interesting solutions. One of the most notable is the idea of black hole hair. Let me explain what that means. There's an old saying in black hole physics: black holes have no hair. This means that black holes are very simple objects. They're completely described by just 3 numbers: their mass, their electric charge, and their spin. It doesn't matter what fell into the black hole to create it. A black hole made from collapsed stars is identical to a black hole made from compressed gas or antimatter or anything else, as long as the mass, charge, and spin are the same. This hairless property is what makes the information paradox so severe. If black holes have no hair, then there's nowhere for information to be stored. The black hole cannot remember what fell into it. But string theory suggests that maybe black holes do have hair after all. Very subtle quantum hair that we haven't been able to detect. In string theory, when strings fall into a black hole, they don't just disappear. They might create subtle quantum patterns on or near the event horizon. These patterns would be incredibly tiny and delicate. You'd need to look at scales much smaller than an atom to see them. But they would be there, and they would encode information about what fell in. Think of it like this. Imagine the event horizon is like the surface of a pond. In classical physics, the pond surface is perfectly smooth. But in string theory, if you look close enough, you see tiny ripples and patterns. These patterns are the hair, the information storage of the black hole. When Hawking radiation is emitted, it interacts with these patterns and carries away the encoded information. The mathematics of this is extremely complex, and string theorists are still working out the details. But the basic idea is that black holes are much more complicated than general relativity suggests. They have rich quantum structure that classical physics misses. And this quantum structure is where information is stored. There's another string theory idea called the fuzzball. In this picture, there's no event horizon at all, and there's no singularity. Instead, a black hole is a tangled ball of strings, a fuzzball. When something falls toward the black hole, it doesn't fall through a smooth horizon. Instead, it gets absorbed into this complex tangle of strings. The information gets scrambled among all the strings in the fuzzball, but it's never destroyed. From far away, the fuzzball looks like a regular black hole with an event horizon. But that's just an approximation. If you could look closely enough, you'd see that there's no sharp boundary. There's just this incredibly dense, tangled configuration of strings. The Hawking radiation comes from the strings themselves, and it carries away the information encoded in their vibrations. The challenge with these string theory solutions is that we can't test them yet. String theory operates at energy scales far beyond what our particle accelerators can reach. The strings themselves are so tiny that we have no way of observing them directly. So, while these ideas are mathematically consistent and might be correct, we have no way of knowing for sure. Let me dig a bit deeper into the fuzzball idea, because it's such a radical reimagining of what a black hole is. Remember, in general relativity, a black hole has a very specific structure. There's a singularity at the center where density becomes infinite. There's an event horizon at a specific radius surrounding that singularity. And there's empty space in between, the interior of the black hole. The fuzzball proposal says this is all wrong. According to fuzzball physics, when a black hole forms, the collapsing matter doesn't create a singularity and an interior. Instead, it creates this complex quantum object, the fuzzball, that fills the entire region where we thought the black hole interior was. Imagine a ball of yarn, but instead of yarn, it's made of vibrating strings from string theory. And instead of being loosely wound, it's wound so tightly and so complexly that it appears solid. That's a fuzzball. It's not empty space. It's not a singularity. It's a quantum object with structure all the way through. In this picture, when something falls toward the black hole, it doesn't fall through an event horizon because there is no event horizon. Instead, it gets absorbed into the fuzzball, its strings becoming part of the tangle. The information about what fell in is preserved in the configuration of strings within the fuzzball. It's scrambled incredibly thoroughly. You'd need to track the quantum state of every string to extract it. But it's not destroyed. The Hawking radiation in the fuzzball picture comes from quantum processes happening within and on the surface of the fuzzball. The radiation is correlated with the internal structure of the fuzzball, which contains the information about what fell in. So the radiation carries away information, and information is conserved. Problem solved. Except there are problems with this solution too. The biggest problem is that it seems to contradict our observations. When we observe black holes, we've actually imaged the shadow of a black hole using the Event Horizon Telescope, they look like they have smooth event horizons, not fuzzy quantum structures. A fuzzball should look different from far away if you observe it carefully enough. But so far, black holes look exactly like general relativity predicts. Fuzzball proponents argue that maybe the quantum fuzziness is so fine-grained that we can't detect it with current technology. Or maybe there are both fuzzballs and regular black holes, and we've only observed the regular kind so far. But these responses feel a bit unsatisfying. The theory makes predictions that don't seem to match what we see. Still, the fuzzball idea is important because it represents a fundamentally different way of thinking about black holes. Instead of treating them as purely gravitational objects described by general relativity, it treats them as quantum objects that need to be described by quantum mechanics. And maybe that's the key insight. Black holes are quantum, not classical, and we need a quantum description to truly understand them. Now, I want to tell you about one of the wildest ideas in recent physics, proposed by Juan Maldacena and Leonard Susskind in 2013. It's called ER equals EPR, and it suggests that quantum entanglement and wormholes are the same thing. If true, this would be a profound unification of quantum mechanics and general relativity, and it might solve the information paradox. First, let me explain what ER and EPR stand for. ER stands for Einstein-Rosen bridge, which is the technical name for a wormhole. A wormhole is a tunnel through space-time that connects two distant regions. It's a solution to Einstein's equations that creates a shortcut through space. EPR stands for Einstein-Podolsky-Rosen, referring to a famous paper about quantum entanglement. Quantum entanglement is one of the strangest phenomena in physics. When two particles become entangled, they become connected in a deep way. If you measure one particle and find it spinning clockwise, you instantly know the other particle is spinning counterclockwise, even if it's on the other side of the universe. Einstein called this spooky action at a distance because it seemed to violate the principle that information can't travel faster than light. Now here's the crazy proposal. Muldesina and Suskind suggested that when two particles are entangled, they're connected by a tiny wormhole. The entanglement is the wormhole. ER equals EPR. Two descriptions of the same underlying reality. You can't send information through these wormholes. They're too small and they collapse too quickly. So this doesn't violate relativity. But it suggests that space at the quantum level is full of tiny wormholes connecting entangled particles. Space isn't smooth. It's a foam of quantum connections. How does this relate to black holes? Well, when Hawking radiation is emitted, the outgoing particles are entangled with particles inside the black hole. In the ER equals EPR picture, this means the outgoing particles are connected to the black hole interior by tiny wormholes. Information can flow through these wormhole connections, allowing the information inside the black hole to gradually leak out in the radiation. This is a beautiful idea because it uses the structure of space-time itself, wormholes, to solve a quantum problem, entanglement and information loss. It suggests that quantum mechanics and general relativity are more deeply connected than we realized. They're not separate theories that need to be unified. They're already describing the same phenomena in different languages. But like all the other proposals, this one has challenges too. The mathematics is still being worked out. We don't know exactly how information flows through these entanglement wormholes, and we don't have experimental evidence that entanglement really is the same as wormholes. It's a compelling idea, but it's still speculative. What's becoming clear after 50 years of work on the information paradox is that all the proposed solutions require us to revise something fundamental about our understanding of reality. Either space isn't what we think it is, or black holes aren't what we think they are, or quantum mechanics works differently than we thought, or some combination of all of these. The paradox is forcing us toward a new understanding of physics. But let's step back from these abstract theoretical proposals and think about the far future. Let's think about what actually happens as the universe ages and black holes slowly evaporate. What will the universe look like when black holes are all that's left? And what happens after the very last black hole evaporates? Let's explore the timeline of the universe's death. To understand the role black holes play in the universe's future, we need to zoom out and look at the big picture of cosmic evolution. Let's start with where we are now and project forward into the unimaginably distant future. Right now, the universe is about 14 billion years old. It's filled with galaxies, and those galaxies are filled with stars. New stars are being born constantly as clouds of gas collapse under their own gravity. This era of cosmic history, the era we live in, is called the stelliferous era, the age of stars. And it's a beautiful time to be alive because the universe is bright and interesting and full of energy. But it won't last forever. Stars form from gas, and there's only a finite amount of gas in the universe. As time goes on, more and more of that gas gets locked up inside stars or gets blown away from galaxies by stellar winds and supernovae. The rate of star formation is already decreasing. Fewer new stars are forming now than formed billions of years ago. In about 100 trillion years, that's one followed by 14 zeros, the last stars will form. After that, no new stars will be born. The universe will have exhausted its supply of star-forming gas. This marks the end of the stelliferous era. But even after star formation stops, the existing stars will continue shining for a while. The smallest stars, called red dwarfs, burn their fuel very slowly. Some red dwarfs will keep shining for 10 trillion years or more. But eventually, even these longest-lived stars will burn out. In about 10,000 trillion years, the last star will fade to darkness. After that, the universe enters a new era. No more fusion, no more starlight, just dead stellar remnants, white dwarfs, neutron stars, and black holes drifting through the darkness. The universe becomes profoundly dark and cold. This is called the degenerate era, because the only objects left are degenerate matter. Matter compressed to the point where quantum mechanical effects hold it up against gravitational collapse. But even these dead stars don't last forever. White dwarfs and neutron stars will slowly cool down, radiating away their heat into space. But more dramatically, they will slowly fall apart. Protons, the particles that make up atomic nuclei, are not perfectly stable. Theoretical calculations suggest that protons decay with a half-life of about 10 to the power of 36 years. That's a 1 followed by 36 zeros. This is an almost incomprehensibly long time. It's a billion years. If you waited that long, half of the protons in any piece of matter would have decayed into lighter particles. Wait another 10 to the power of 36 years, and half of the remaining protons decay. And so on. In about 10 to the power of 40 years, most protons will have decayed. White dwarfs will evaporate as their atoms fall apart. Neutron stars will dissolve. Any planets or asteroids still around will slowly disintegrate. Everything made of ordinary matter will decay into radiation and lighter particles. This marks the end of the degenerate era. And what's left? Only black holes. By 10 to the power of 40 years in the future, black holes will be the only large-scale structures remaining in the universe. Everything else, every star, every planet, every atom, will have decayed away. The universe enters the black hole era. Let me paint a picture of this unimaginably distant future. The universe is about 10 to the power of 40 years old. That number is so large, it's almost meaningless. The current age of the universe, 14 billion years, is to this future time, as a single second is to a trillion times the current age of the universe. The timescales are so vast that our intuition completely fails. In this far future, the universe is dark. No stars shine. No fusion reactions occur. The cosmic microwave background radiation, which now fills the universe at a temperature of about 3 degrees above absolute zero, has cooled to nearly absolute zero itself. The universe has expanded so much that galaxies have become isolated islands separated by incomprehensible distances. Most galaxies are no longer visible to each other. Within each galaxy, or rather within what was once a galaxy. Black holes drift through the void. The supermassive black hole that once sat at the galaxy's center is still there, grown even larger over the eons from swallowing the remnants of stars. Smaller stellar mass black holes are scattered throughout the region, the ghosts of individual stars that died long ago. These black holes are not completely unchanging. They orbit each other, very slowly, pulled by their mutual gravity. When two black holes orbit, they emit gravitational waves, ripples in space-time itself. These waves carry away energy, causing the black holes to gradually spiral inward toward each other. Eventually, after unimaginably long times, black holes will merge with each other, creating larger black holes. Over time, scales of 10 to the power of 20 years or more, the black holes in each galaxy-sized region will merge together into one enormous black hole. The universe becomes populated by isolated supermassive black holes, each one the final remnant of what was once a galaxy. And then silence. Almost nothing happens. The black holes just sit there in the darkness, separated by vast distances, with nothing happening around them. Except they're not quite unchanging. They're evaporating. Through Hawking radiation, each black hole is slowly losing mass. The process is incredibly gradual. A solar mass black hole emits about 1 photon every few minutes. A supermassive black hole emits even less. But it never stops. Slowly, imperceptibly, the black holes shrink. From a human perspective, nothing would appear to be happening. You could watch a black hole for billions of years and see no change. But the change is there, accumulating. The black hole is dying, one quantum of radiation at a time. This is the black hole era, a time when black holes are the only significant structures in the universe, slowly evaporating in the darkness. It's a time of almost unimaginable stillness and emptiness. If consciousness could somehow exist in this era, it would experience a universe that's essentially frozen, where nothing interesting happens for timescales longer than the entire current age of the universe. But it doesn't last forever. Eventually, the black holes evaporate completely, and when they do, even these final structures vanish, leaving behind only photons expanding through empty space. Let's focus on a single black hole in this far future and watch its final death. We'll imagine a supermassive black hole once at the center of a galaxy with a mass of about 1 billion times the mass of our Sun. This is a fairly typical mass for such black holes. According to Hawking's calculations, this black hole will take about 10 to the power of 98 years to evaporate completely. That's a 1 followed by 98 zeros. To give you any sense of scale, if every atom in the observable universe represented a year, that still wouldn't be enough time. This number is so enormous that it defies comprehension. For almost all of that time, the black hole barely changes. It sits there, emitting a tiny trickle of radiation, its temperature just a tiny fraction of a degree above absolute zero. To any observer, it would seem eternal. Its mass decreases, but so slowly that you couldn't measure the change, even if you watched for trillions of years. But as the black hole gets smaller, the process accelerates. At 1 billion solar masses, it evaporates very slowly. When it's shrunk down to 10 million solar masses, it evaporates 100 times faster. When it reaches 10,000 solar masses, it's evaporating 10,000 times faster than it started. The acceleration is relentless and exponential. In the final trillion years of its existence, a time span that seems impossibly long, but is actually just a tiny fraction of the black hole's total lifetime, the evaporation becomes noticeable. The black hole shrinks visibly. Its temperature climbs from near absolute zero up to thousands of degrees. It begins to glow with visible light. In the final billion years, the black hole is now relatively small, perhaps just 1,000 solar masses. It's hot, glowing brightly, emitting enormous amounts of radiation. It's shrinking faster and faster, getting smaller and hotter and brighter with each passing moment. In the final million years, it's down to the mass of a single star, burning with the luminosity of a supernova. In the final 1,000 years, it's the mass of a large asteroid, but its temperature is millions of degrees. It's a brilliant point of light in the darkness, shining across the empty void. In the final year of its existence, extraordinary things happen. The black hole is now small enough that you could hold it in your hands if you could somehow survive its radiation and gravity. But it contains as much mass as a mountain, and its temperature is billions of degrees. It's emitting gamma rays, X-rays, every form of radiation at an incredible rate. It's radiating away its entire remaining mass as fast as physics allows. In the final second, the black hole releases as much energy as a large star releases in its entire 10 billion year lifetime. The event horizon shrinks down to microscopic sizes. The temperature soars to trillions of degrees, hotter than anything that has existed in the universe since the first moments after the Big Bang. And then, in a final flash of gamma rays and elementary particles, the black hole vanishes. The singularity evaporates. The event horizon collapses to nothing. Where there was once a black hole, there's now just a burst of radiation expanding outward at the speed of light. In an instant, the last structure in that region of the universe has disappeared. Nothing is left but photons and a few elementary particles flying apart from each other, growing more distant with every passing moment. And this happens to every black hole. One by one, separated by incomprehensible time intervals, each of the isolated black holes drifting through the void undergoes this same death. The last one evaporates, and then there are no black holes left. The black hole era is over. So what remains after the last black hole has evaporated? Let's think about what the universe looks like at this point. We're now at about 10 to the power of 100 years after the Big Bang, a time so far in the future that it makes the black hole era seem recent by comparison. The universe is now filled only with radiation, photons mostly, flying through space, separated by enormous distances. There are also some elementary particles, electrons, positrons, neutrinos, but they're incredibly rare and spread out. The average density of the universe is essentially zero. Space is, for all practical purposes, empty. The temperature of the universe is incredibly close to absolute zero. The photons have been redshifted by cosmic expansion for so long that their wavelengths are longer than the size of the observable universe. They carry almost no energy. Everything is cold. Everything is still. Everything is spread out. This is called the heat death of the universe. It's the state of maximum entropy, maximum disorder. And in a maximum entropy state, nothing can happen. You see, for anything interesting to occur, for any process to take place, you need a difference in energy or temperature or some other property. You need a hot region and a cold region. You need concentrated energy and empty space. You need order and disorder. But in the heat-death state, everything is uniform. There are no gradients, no differences, no structure. The universe has reached thermodynamic equilibrium, and in equilibrium, nothing changes. Time continues to pass, but nothing happens. It's like a movie that's frozen on a single frame forever. Could anything come after this? Some physicists have speculated about possibilities. Maybe quantum fluctuations could spontaneously create a new Big Bang somewhere in the void, starting a new universe. Maybe the universe could quantum tunnel to a lower energy state in a process called vacuum decay, releasing enormous energy and transforming the nature of space itself. Maybe there are physical processes we don't understand yet that could create structure from this maximum entropy state. But based on our current understanding of physics, the heat death is truly the end. Once the universe reaches this state, it stays in this state forever. Time continues, but nothing happens. No stars shine, no black holes exist, no structures form. The universe is dead in the deepest sense of the word. And this brings us full circle to where we started. Are black holes eternal? We've traveled through the entire timeline of the universe from now to its ultimate end. And what we've learned is that black holes are the last things to die. They outlast stars by incomprehensible factors. They outlast atoms. They outlast every other structure in the universe. But ultimately, they do die. They evaporate. They vanish. Nothing is eternal, not even black holes. So after 2.5 hours together, after exploring the physics of black holes, the mystery of Hawking radiation, the profundity of the information paradox, the wildness of proposed solutions, and the far future timeline of the universe, we can finally answer our title question with clarity and understanding. Are black holes eternal? No. Black holes are not eternal. They emit Hawking radiation, they lose mass, and eventually they evaporate completely. Given enough time scales that are almost incomprehensible, longer than trillions of trillions of trillions of years, every black hole will die. But here's what makes this answer so interesting. Black holes are the longest-lived structures that can exist in our universe. They outlast everything else. Stars burn out in billions of years. Planets crumble over trillions of years. Even protons decay in about 10 to the power of 36 years. But black holes last for 10 to the power of 100 years or more, depending on their mass. In a very real sense, black holes are the closest thing to eternal that the universe can produce. They're the final form of matter, the last stage of cosmic evolution. Everything else decays first. Only black holes remain in the deep future. They're the universe's last gasp before the final heat death. And yet they do die. That's what Hawking discovered. That's what shocked the physics community. The most permanent-seeming objects in existence have an expiration date. They glow, they shrink, they vanish. Nothing is truly forever. But answering whether black holes are eternal doesn't resolve the deeper mystery we've been exploring. In fact, it opens up an even more profound question. The information paradox remains unsolved. We still don't know how information escapes from black holes. We still don't know which of our fundamental theories needs to be revised. Think about where we've traveled. We started with a simple observation. Black holes emit radiation. We discovered this creates a paradox. Information seems to be destroyed. We explored wild solutions, firewalls, holograms, fuzzballs, wormholes. But none of these solutions is proven. None of them is universally accepted by physicists. The mystery remains open. What this tells us is that our understanding of reality is incomplete. We have two magnificent theories: general relativity and quantum mechanics. Both work incredibly well in their respective domains. But when we try to combine them, when we apply both to black holes, we get contradictions. This means something fundamental is missing from our understanding. Maybe space and time are not fundamental but emergent from something deeper. Maybe information exists in ways we haven't imagined. Maybe quantum mechanics works differently at extreme scales. Maybe black holes are not what general relativity tells us they are. Or maybe all of these things are true in ways we don't yet understand. The information paradox is telling us that we need a new theory. A theory that successfully unites quantum mechanics and general relativity. A theory that explains what really happens at the event horizon of a black hole. A theory that resolves the paradox and shows us how information is truly conserved. Physicists call this hypothetical theory quantum gravity, and finding it is one of the great quests of modern physics. Let's zoom out and think about what all of this means beyond just black holes and physics. What does the information paradox tell us about the nature of reality and our place in it? First, it tells us that the universe has structure all the way down. We might have thought that black holes were the end of the story, infinitely dense singularities where physics breaks down. But the information paradox suggests there's more going on. Black holes have subtle quantum structure that we can't quite see yet. Reality is more complex than it appears, even in the most extreme conditions. Second, it tells us that information might be the most fundamental thing in the universe. More fundamental than matter, more fundamental than energy, maybe even more fundamental than space and time. Information is conserved absolutely, suggesting it's the bedrock upon which everything else is built. You, your consciousness, your memories, all of that is information. And maybe, just maybe, that information is truly eternal in some form. Third, it reminds us of how much we don't know. We've accomplished amazing things in physics. We've understood the atom, mapped the universe, detected gravitational waves, but we still can't resolve a paradox about black holes that was discovered 50 years ago. We're still puzzling over basic questions about the nature of reality. This should fill us with humility and wonder. The universe still has secrets. And finally, it shows us that asking questions leads to deeper questions. We asked if black holes are eternal. That led us to discover Hawking radiation, which led us to the information paradox, which led us to question the nature of space, time, and information itself. Each answer opens up new mysteries. This is how science works. It's not a process of getting all the answers, it's a process of asking better and better questions. Let me leave you with one last thought to ponder. Right now, in our era of cosmic history, black holes are relatively common. There are millions or billions of them in our galaxy alone. Stars are still shining. The universe is bright and interesting and full of activity. In the cosmic timeline, we live in an era of abundance and energy. But in the unimaginably distant future we explored, black holes become the only structures. Everything else has decayed away. The universe becomes defined by these evaporating black holes, the last holdouts against the inexorable march toward entropy and heat death. And then, one by one, even they vanish. The last black hole flares up in its final moment, releases its energy into the void, and disappears. And the universe continues, now truly empty, with nothing left to mark the eons that came before. It's a melancholy picture in some ways, but there's also beauty in it. The universe tells a story. It has a beginning, the Big Bang. It has a middle, our current era of stars and galaxies. And it has an end, the heat death after all black holes evaporate. We've been privileged to figure out this story, to read it in the mathematics of physics, to understand our place in cosmic history. Black holes aren't eternal, but maybe, just maybe, the information that falls into them is. Maybe every book that's ever been written, every thought that's ever been thought, every moment that's ever been experienced, maybe all of that information is preserved somewhere in the structure of the universe, encoded in ways we don't fully understand yet. Maybe nothing is truly lost. Maybe the universe remembers everything. And on that note, thank you for taking this journey with me. If you enjoyed exploring one of the deepest mysteries in science, I hope you'll share this with others who might appreciate it too. Leave your thoughts in the comments. Tell me what blew your mind the most. And remember, the universe is stranger and more wonderful than we can imagine. And the fact that we can even begin to understand it is perhaps the most amazing thing of all. Black holes aren't eternal, but our curiosity, our drive to understand, our capacity to ask profound questions about reality, maybe those things can last as long as conscious beings exist in this universe. And that might be the closest to immortality that anything can achieve.